Well, there's a few news articles you might like. This one I thought is pretty good, and we'll talk more about it. As the cryptocurrency market heats up, it just stops making any sense. And people are betting on things that are held up by nothing logical, so it's really just random. So just going along with whatever's fashionable can make you a pile of money. So like he says, just being an idiot can lead to making money. Of course, that's always been true. But right now, with cryptocurrencies and NFTs, what you're doing is just trying to make money based on something being popular, and not for any other reason. So Trump announced when Twitter and Facebook kicked him off months ago that he was going to make his new social network. And now he has, and apparently I hope they charged a lot of money for this, because this is his new social network. This is a blog circa like 1998. That's it. No, you can't even put comments on it. It's just a series of blog posts by Trump sitting on a static web page. It looks like they built some kind of engine, so it's a little bit more than just adding HTML every time. He's got up to sort of Blogger version 1. Anyway, that's his new social network, at least so far. All right. And so this woman, Sparks, decided that she couldn't stand having people post false information about the vaccine and coronavirus on TikTok, so she made opposing TikToks explaining why people are lying and what's wrong about it. And what happened is she got the right-wing army mad at her. And as many, many other people have found out, especially women, if you offend the right wing, they will come after you. So they tracked down her home, they threatened her children, they posted pictures of them, they sent an endless flood of it to everybody she knew, saying they were going to kill her and rape her and burn down her house and everything else. And this is very, very common. So she left the platform, but then she said, no, it's my duty to go back and continue. It is the sad state of America at the moment that both sides are very, very, very angry, and there's an awful lot of extremists on the right that are the major terrorist threat we've had for quite a while now. And people like Mitt Romney found out that the behavior of modern right-wingers is not even up to basic politeness standards anymore. This is very reminiscent of the the Civil War, and people just got very, very, very angry until they start losing all discretion and all politeness. So this January 6th event was so troubling that they would like to do something about it. But the problem is, of course, that the anti-terrorism Department of Homeland Security is not allowed to monitor citizens without something like a search warrant. So they're planning to do an end run around it. They're going to outsource it to some company who doesn't have to obey those laws. I wonder if this will actually hold up in court. But anyway, that's what they're going to do. If they outsource tracking terrorists to a private company, then the private company is not held to the Fourth Amendment. And so I guess we'll see how that works. Of course, the big question that many people have been asking ever since January 6th is everybody that pays attention to Facebook or Twitter knew that this was going to happen, or even just watched Donald Trump's speeches and statements, but the Capitol Police seemed completely unprepared. So apparently the official channels are not as smart as just amateurs watching Twitter and Facebook, and they need to do something about that. Although there's clearly a huge problem with people inside the system that are in favor of this, so they can't even get their act together to form a report on how this happened. So again, like the Civil War, that's disturbing. There was a network error. I wonder if that's okay. My machine gave me a network error, but then it came back. Hope you people can see the Twitch anyway. All right, so Gemini is a trading platform, and they've added Dogecoin. Okay, good. I'm glad you can see it. And the trading frenzy was so extreme, Robinhood crashed again. You couldn't buy or sell Doge. It exceeded their limit of capacity. So Doge is going up and down, and certainly when Elon Musk appears on Saturday Night Live, it will have another wild swing up and down. So because there's absolutely nothing holding Dogecoin to any particular price. it's just like pet rocks. It's an arbitrary thing that has no intrinsic value and not connected to any profit or any real world issues like a shipment of goods or anything. So there's no reason for it not to jump up and down by a huge amount, and that's what it does. That's what's called risk in financial services, is the variation of something over the mean. And all cryptocurrencies are high-risk investments because they vary a lot and follow no real pattern. So it's a real gambling game to get into them. So here is a very interesting claim by this company. Interesting to me because I've heard this story before. This guy claims that he is connected to the ISPs and monitoring traffic, and he can now see that 80 to 90% of the Standard & Poor's 500 companies are already infected with malware, and they don't know it. And this is exactly what our crooked chief technology officer did about 10 years at City College. He hired a consultant to do exactly the same analysis, to look at the network traffic and then claim that he saw malware beaconing home and that he was detecting it with a secret proprietary system that we could not inspect or audit. And it meant that all our machines were totally infected with viruses that were 10 years old, and everything had been infected for 10 years without us knowing it. And this turned out, it took us about a year to battle him and force him to give specific claims we could test, and this all turned out to be false. And we pushed that guy out, and I gave talks at DEF CON and everything about it. We were never able to see inside his system, but what I believe is going on is he's looking for what he thinks is malware beaconing, which is traffic going to IP addresses that are known to host malicious command and control servers. But it's not true that all traffic going there means you're really owned. So anyway, it sounds like this guy's done something similar, although I really don't know what he's done, but I've heard this exact claim before. If you do network forensics wrong, you have a bunch of false positives and you think people are infected when they aren't. And that seems a whole lot more likely to me than really that 80 to 90% of the top companies are infected and they don't even know it. Tether is the most important cryptocurrency of them all, largely. Tether is the one that is printed by the billions every month to prop up the price of cryptocurrency. This is why Bitcoin goes up. They print fake dollars and they buy it with fake dollars to pump the price up. And Tether keeps claiming that it's a stable coin tied to the value of a dollar, backed by a reserve, but they can never prove that, and all the auditing companies keep quitting and claiming it's not true. It's not based by anything. They just print fake dollars like monopoly money and buy Bitcoin with it to prop up the price. So Tether is the main pump and dump scheme technique on the entire cryptocurrency marketplace, used to manipulate prices, and now Coinbase is going to let you buy Tether. So it's like I say, that in the last 3 months, these outrageous scams that every serious professional would never touch have moved into the mainstream. So for better or worse, this is going to be mainstream economics from now on, including these things. This is also what happened after the last pandemic in 1918. This is how we got the Roaring '20s. They had a crazy financial market where everybody could buy stocks on margin and everybody felt rich before it all crashed in '29. So it looks like we're going to do the whole thing again. Anyway, here we are at 126. And so it's kernel debugging today, which we've talked about a bit, but I've got more about it now, and I'll demonstrate the project I just wrote, which is an update of the 2 Windows kernel debugging project to work with local VMs. It didn't seem to work quite the same with local virtual machines as it did when I wrote it a year ago on Azure. So I made it into 2 separate projects, and I'll demonstrate the local version. So let's take a look at that. So here we are. Kernel debugging. All right, and we talked about this before. OllyDbg, or the equivalent product Immunity Debugger, is the most popular debugger for user mode analysis, or for that matter, x32 or x64 debug. That all work very much the same way, but you can't use them for the kernel. For that, you must use WinDbg. You can do user mode or kernel mode with WinDbg. So, device drivers are a way for a third-party developer, like the designer of a printer, to add code to the Windows kernel. Because the printer is hardware that didn't come from Microsoft, it needs to be paired with software that didn't come from Microsoft to control the hardware. And that has to be in the kernel so it can have direct access to the hardware. So this is why it makes Microsoft very nervous. They're responsible for most of the blue screen errors. Drivers load in memory, stay resident, respond to requests from applications, and if the drivers have bugs, then the whole system crashes because they're in the kernel, and you can't recover from a kernel crash. So applications cannot directly access the kernel driver, of course. They access a device object in user land, which sends requests to the device. So here you get Microsoft's strange naming convention. As I mentioned before, the simple rule is everything in Microsoft Word is named the opposite of what it is. So a device is not a hardware object like a printer. A device is a software handle to manipulate that object. So your device is like drive letter C:, and that points to a hard disk indirectly. So a driver creates the device, and then users can send data to the device, which will then send it to the driver, which will then send it to the actual hardware. So if you plug in a USB flash drive, Windows gets a driver somewhere, either by prompting you to download it or by recognizing that this particular device is on a list of things that it already has a driver for, and then it gets the driver to create a device object and give it a letter. Now you have a device like F, and now application can read and write to F, and they will be communicating with the hard flash drive. If you plug in a second flash drive of the same brand, it will call the same driver and create a new device called G, and now there are two devices pointing to the same driver but going off to different hardware flash drives. All right, now remember, this is kind of like DILs, but it's not the same because it happens in the kernel. So in DILs, you have a library that contains something like internet functions or some other function you want to use, and they export functions using their export table. So when a function loads the library, it calls DIL main, which is what prepares the DIL for use, and then it stays in memory and various functions can use it. When you load a driver is loaded into the kernel. For example, when you plug in a USB flash drive and it says, oh, I better put that driver in the kernel, it loads it into the kernel as a loaded module, and then it calls driver entry, which is the analogous procedure to DIL main. That's the routine that should be run when you first load a driver to prepare it for use. These prepares these things called callback objects. All right, and so it defines a callback object through which other drivers can request notification of condition and so on. That's how it works. So DILs are loaded in user-landed memory when a process is launched, and they execute DIL main. Drivers load into the kernel when you add hardware. Then they execute driver entry, and they prepare callback functions and callback objects. So driver entry is what registers the addresses for callback functions. So that now Windows will create a driver object structure in the kernel and passes it to driver entry, which fills it with callback functions. And that's it. Now driver entry now then creates a device which can be accessed from user land, and now your program can use it. So for a normal read request, your user mode application will obtain a file handle for the device called read file. The kernel will process the read file request and then invoke the driver's callback function, handling I/O to read the file. Now, if you do a malicious request from malware, it often goes from device I/O control. This is a generic request, just a less obvious way to do it, and it can send data and receive data from the object. So you have a malicious program that might go through kernel 32, or it might use the native API and go through NTDIL. Then it goes down to the kernel, which then goes to the malicious driver and kernel data structures to the hardware. All right, there is some kernel mode malware that has no significant user malware at all, although I think this is not true of modern versions of Windows. The last statement I've seen is that modern versions of Windows have essentially eliminated kernel mode malware. I'm relatively suspicious of that, but that was at least considered true a couple of years ago. They certainly have made it much harder. I don't know if the bad guys have yet figured out how to write some modern kernel mode hardware that can get software that can get in there. So, all right. Malicious drivers typically interact with NTOS kernel or HAL, the hardware abstraction layer, to connect to the hardware, and imports functions from these to manipulate the kernel. All right, all right, just a few terms to learn. Let's take a look at some Cahoots. And even though I only have like a vague understanding of what those terms mean, you know, the main thing is to recognize them, and then you are more prepared to deal with instructions you find later to use them. Well, if you have only 4, you have a high chance of winning. And that appears to be the case. All right. All right, so what is it an application interacts with? The application can only see the device object, which is the software thing like C or D. Software object-oriented programming object in that sense that points to these other things. All right, so what code is loaded into a process? That's a dill, good. All right, when a driver is loaded, what procedure is called first? Driver entry is what starts a driver. All right. And which one of these runs in user mode? The fundamental rule, you see, is everything is always named the opposite of what it is. Kernel 32 is not in the kernel. All right, good. All right. So, to do kernel debugging, you can do it with virtual machines if you have 2 of them. Then you can configure a virtual serial port. That's the way we used to do it. But these days, with modern versions of Windows, we can use IP networking to connect them, which is easier. That's what I'll do tonight. In the old days, before Windows Vista, you would edit boot.ini, and that's still in your book. But nowadays, Microsoft removed that kind of bootloader, and now it uses bcdedit to control the boot configuration data store, which is a binary store that serves the same purpose. So you use things like this, bcdedit debug on, in an administrator command prompt to turn on debugging. You need WinDbg, which we're going to use WinDbg Preview, which comes from the Microsoft Store, but you can also go online and get the old WinDbg, and we've used them both in different parts of this class. You just install it with the Windows Software Development Kit. You can install debugging tools. All right, or you can run livekd with the old WinDbg, and then you can do the kernel debugging as we did before on one machine, where you're examining a read-only copy of the debugger, which is really done by sort of stimulating a crash dump and examining the crash dump. That's what livekd does. And then you can examine the symbols and such in WinDbg, but you can't put in breakpoints and stop it, which is what we're going to do tonight. All right, and we know the command line commands, we talked about them before. You can read data from an address. You can display it as ASCII, Unicode, or double-bit words. Or you can do db to show it both as hexadecimal bytes and ASCII. You can edit memory. You can write in any format you want to areas of memory, same as you could in any other full-featured debugger. And you can, of course, use all the arithmetic operators to do calculations and such. This will show the first argument of a function as a wide character string. All right. You can set breakpoints with BP. You use G to go to run it. And so this will set a breakpoint at a certain address. This will it'll break when this function is called, get proc address, and then it will execute this script every time it breaks, which will display in ASCII a certain region of data and then go again. And if you're working in Azure, you can get this working. I was unable to get this working on our local machines, but I tried today. Something that would automatically capture all calls to read or write files and print out the name of the file, which is kind of cute. You can write these little spy programs in the debugger that print out certain kinds of data, which is pretty cute, but it didn't seem to work with local Windows 10 machines. Remember, livekd cannot use breakpoints because you're just looking at a static image of the kernel, not the real kernel. List module is probably the first thing you do. It shows all your modules. So this M lets you look for the particular modules matching this pattern. So this will show me the disk, which is the disk driver. You can read from memory. This will show the start of a module. This will show the first 10 in hexadecimal words of the module to disassemble modules. And so here's DDNT, and here's DDNT, limiting me to the first 10 hexadecimal, which I guess it interpreted as 10 32-bit words, because this is 16 32-bit words, and that's what this is, 10 in hexadecimal. All right, and .hh is the best way to get help with the old Windows 3.1 chum file, which is the most accurate help page to teach you WinDbg, and we've talked about this before. R will dump the registers. All right, let's take a look at another set of cahoots. All right, that might be it. I'll wait a few seconds and see if we do have more, okay? All right. All right, so what command sets a breakpoint? BP, that's good. All right, what command will show memory as ASCII? Display as ASCII. Good. All right, which one shows kernel drivers? Okay, LM shows your loaded modules, including the drivers. All right, and which command will change memory? Okay, that's edit. All right. All right. All right, and then we got to worry about symbols. The symbols, of course, make it much easier to refer to areas. Instead of having to refer to hexadecimal addresses, you can refer to a meaningful symbol of a Microsoft label, like this is the create process address space. So you can have module name, bang symbol name to refer to any thing that has a name, module name, or just the symbol name, and so on. NTOS kernel is the one that lets you use an abbreviation of NT. So this will unassemble the NT create process function. All right, so we've already done this before. I think you can unassemble it. You can limit it to 10 or 20 bytes. I think it's bytes here instead of words. Anyway, then you can set a breakpoint as soon as this module is loaded. Here's a function that finds the entry point of a module, so this is how you put a breakpoint on the entry point of this driver. And then that driver will never run, it will break as soon as it loads, and this is what you might do if you were trying to debug a driver you're writing, where you want to see what it looks like and then step through it step by step to see how it works. You can use X to search for things. You can use wildcards with stars in here like before, and this will show you all the kernel module NTOS kernel functions, labels really, that contain create process. You can use LN to find the nearest label, nearest symbol. So if you're at an address and you're not sure what's going on, it'll find symbols nearby which might give you a clue what function you're in. DT lets you see structures. So you can have the same kind of syntax to show how you're going to print out the structure. So if you do DT NT bang underscore driver underscore object, this will show you the template for the driver object structure. And so it shows you the number of bytes, running total of the number of bytes, and the various things here. So this is a 32-bit pointer to device object, and so it takes 4 bytes. And so it gives you the layout of the structure. And all right. So you can see driver object and device object, both in the function. This is why nothing can be hidden from you very much. And then you can load, you could load the driver object, but then you can load this particular data where it's going to start, and now it will take the structure and it will lay the values it found at that address. So you'll see the exact layout of this driver, and this is the beep driver, and the easiest thing to see is the driver name, which has a readable string driver beep. All right, driver init is what's called when a driver is loaded, and you can see that line here. Driver init is down here. So there's the address, which points to the thing that will run when you first load that driver. And of course, as we just saw when we used Metasploit to make a malicious DIL, it just put the malware right in DIL main. And I don't know, didn't get around to this. It'd be a fun thing to see if Metasploit can make malicious drivers. and just stick the malware in driver main, it might. I'm not sure, but that would be a logical thing to do. All right, so you can just automatically download symbols. They can be cached locally. We're going to do that when we get to the demonstration later. We don't have to manually download them, especially in WinDbg Preview. It's pretty easy to download them automatically. So you get those symbols, which makes it much easier to debug the kernel and the user land for that matter. So let's try 10C. All right. All right. How do you set a breakpoint? B, one starting at B. This, I think, makes a deferred breakpoint at the start of that function. All right, what command will show you the type information for a structure? Yeah, there's dog barking outside. My neighbors are taking their dog out. Yep, this is the one that views the structure of the driver object. Display type, I think. All right, what command lists all the functions in NTOS kernel? Nah, there is not a chicken around here. There's crows, though, but no chickens. Okay, that's it. Examine all symbols in NTOS kernel, including all the functions. All right. Right. All right, so in practice, you can look at a program that writes to files from kernel space as an example of how this works. So kernel mode programs can't call user mode functions. They must use the kernel mode versions of these files. And so your user space code will create a service with create service. You see that down here, create service, and all the rest of this is pushing stuff on the stack to be the arguments for that call. And you see up here the service type is a type 11. I guess that's 1 is all it pushes. This is a label 1 for the label of the footnote. And so this is a kernel driver type service. So this service will load a kernel driver, and then it will call create file and get a handle to a device object. then once it has a handle to device, it can use device I/O control, which we talked about before, to send data to the driver. So that's what it looks like in user space. In the kernel mode code, you can use WinDbg, and you'll see every kernel module that loads, and you can see them as they load, and you might be able to spot an extra one loading, which would be the malicious one. And so the filewriter.sys driver loads in the kernel. That's the malicious driver. One thing to be aware is if you're using VMware, you'll see kmixer.sys loading and unloading all the time. That's normal. That is something used by VMware itself. It is not malware. But it's not a Microsoft product either, so I don't think Microsoft documentation is likely to warn you about it. All right, so drv_obj shows you a driver object. So you can see file writer, and here you go. It tries to find symbols, but it can't find symbols because that's not a Microsoft product where there's a Microsoft symbol table online. That is a malware product, and there probably are no symbols available anywhere. And then it will show you it starts here. So you can use DT to see its structure. And you see this is a device object with the usual structure, but by adding this address, you see the specific values here, and here you see it's a thing called file writer, and you can see various other values, but it's not immediately obvious what they mean. All right, so if you step through that function, it'll eventually create this file using DOS devices, which is, of course, a direct reference to the hardware, and then a secret file. That's a fully qualified object name. Again, not the normal way to do it, but that's what happens when you use that IO writer function instead of the normal calls that would just refer to like the normal path starting with C. So it's going to create a thing called secret file.txt, and that would be where something the malware is using, like a label that this machine is infected or stolen keystrokes or something like that. So applications work with devices. So you look at your user space application to find the device object. Then you find the driver object, and you can find out more about it and the handles that use it. So you can track it down by debugging once you have a clue that there is a malicious thing in user land creating a malicious object in kernel land. And then there's rootkits. Now the point of a rootkit is to subvert the entire operating system at a very fundamental level so that you can hide processes from other processes. The original rootkits in Linux would affect init. When you first boot up a Linux system, the first process is init, and all future processes are forked from init. So if you can alter init, you alter the fundamental start of the operating system right from boot up. And you can make it do something, and the goal point is when you're all done, you'll have antivirus running, but antivirus will no longer have access to the whole file system because you perverted the API calls that control access to the file system. So that's the plan here. Now, it used to be before, I think around Vista, that a lot of rootkits were in the kernel. And the most popular method, which I used to have in this class, was system service descriptor table, but I took it out when I got rid of Windows 2008, which is no longer supported, which is the last time that I know that this technique worked. But the SSDT hooking looks like this. This is a table that points to the system services in the kernel. Now, if you want to call the kernel, as we've done in other classes, you can call int2e, sysenter, or syscall. These are assembly language functions that will call the kernel. And then, of course, there'll be arguments in the registers or the stack. I think in this case, just registers that tell it which kernel function you're trying to call. These days, sysenter is the modern preferred way, and the function code is stored in the EAX register. So here's ntdil.dil, and so you see here it is calling sysenter. So up here someplace it put a 25 in EAX, and then it called sysenter, and that's going to call ntCreateFile. And it'll find the other parameters like the file name and such in the other objects that are being created here. So when you do call ntCreateFile, it doesn't jump directly to the function, it jumps to the SSDT table. And the SSDT table just has a series of entries, each 32 bits long for 32-bit Windows, and this points to all the Windows NT calls. The reason why this is there is because suppose that Microsoft wanted to update the kernel with like a Windows update, and they wanted to change the size of a kernel function, but it wouldn't fit in the space allowed for it, so now they have to move it to some other location. They have to have some way to tell programs that are already compiled on your machine how to find the new modified function. So they would modify the function, and then they would change this value to point to the location of the new function. And that way they can update the operating system underneath compiled code, and it will still work. That's why you have to have this layer of indirection here. And so that's the purpose of the SSDT. And it's been around forever. I remember looking at the same thing in the Commodore VIC-20 in the early 90s. It had the same thing. All right, so if you want to modify the operating system so create file no longer does the usual thing, then you just hook it. And so you change the value of the pointer to ntcreate file, and then it goes to some code that you've been able to inject. And so now usually it's very easy to detect because the kernel is not very big. You know, the machine I did this on, the whole kernel was from 804 to 806. So anything with an address that's not in that range is not a real Windows kernel. So you can list all the modules. You'll see the SSDT table. There's another command I found that worked, was this longer command that shows it. And then you can see the SSDT table. So here's the address just counting up 4 bytes at a time. Here's the contents that point to addresses. And here's the function. And you see all these start with 82 because these are the legitimate unaltered entries that point to the real location of NTOS kernel in the RAM of this Windows 2008 machine I did it on. So here's the SSDT table. You can dump it another way where you just see the values. And you notice these are all 805, 805, 806, and this one is F7A. So this is the hooked one that points to a ridiculously very different entry. So that is clearly not pointing to the genuine kernel function, but pointing to something else, and that's what hooking does. Now, hooking is what malware does. It's unfortunately what security products also did at this time, things like firewalls and antivirus, which is why Microsoft gradually got more and more fed up with everybody and their brother messing with the kernel and started to lock more and more people out of the kernel because, of course, these products would conflict with Windows updates and cause blue screens of death. So you can load drivers in LM and see them all, and then see if you find something that shouldn't be there. All right, so here's the listing of the rootkit hook function. And so what it does is it jumps to the original ntcreate file function down here, but it does something first to like decide if I want to lie to you and then execute some sort of lie, but if not, then go run the original file function. So of course, most of the time it works. Otherwise, it would just break the operating system instead of making a small modification like hiding certain files from the antivirus, which is what you probably want it to do. All right, interrupts cause programming to jump from what it's doing and do something else and then come back. And you can register a handler for interrupt code, and then when that interrupt is called, it will run to that handler. That's an interrupt service routine. And there's an interrupt descriptor table that serves the same purpose as the SSDT. And so here you have, again, an interrupt descriptor table counting up, and you see the point to all these handlers for various interrupt codes that might come out. All right. So if you want to, there's a tool here that will load a driver just for testing it. And as I mentioned, Microsoft kept putting more and more defenses in it. So BCD Edit is the product used now instead of boot.ini. And now 64-bit versions now have Patch Guard, which prevents third-party code from modifying the code. So you can't do this SSDT or IDT stuff anymore. You can turn it off, but it's on by default. And Microsoft has done that intentionally. They also have driver signing now. You can't just put a driver in there. The driver has to be signed, and therefore you have to know who made it and verified, with the usual signature verification with trusted certificate authorities, so that they can find out who you are and sue you and put you out of business if malicious things are being signed with your code. And for the last 5 or 6 years, I've been hearing about some malware that actually signed with stolen keys. So sometimes companies get their keys stolen, or maybe they take bribes and sell them or something, and it's actually used to sign malware, but you can't do that very much, or the people that sell your driver signing certificate will cancel it. And I've got one. It's not easy to get. It's not easy to keep, so you try to protect it so bad people don't use it. You can disable driver signature enforcement in BCD Edit for your operating system, but of course if you do, it's a lot less safe to run. All right, and let's take a look at the last cahoots. I've done that quite a lot when I'm putting a server operating system on old junky hardware with old junky drivers, which is certainly not what Microsoft recommends, but what I often had to do in the lab to set up a machine for students to use. Syntax error. That's right. All right, so which module is loaded and unloaded in virtual machines? Yeah, it's pretty good music. I'd like to have the real Jeopardy music, but it would probably violate copyright. Anyway, that's K-Mixer. If these guys go broke, I could go back to the one I wrote and put in Jeopardy music, but of course the one I write is not so pretty. Anyway. All right, what's the normal function used to execute kernel code? This is the normal assembly language command, really. Sysenter is the modern command they recommend using. All right, what object is altered by rootkits, at least in 2008? That's the SSTT. It was a fun lab, but I took it out because it's out of date. All right. Which one of these is not used in Windows 10? Okay, boot.ini, not used in any modern version of Windows. All right, if you want to use unsigned drivers in 64-bit Windows 10, what should you do? That's no integrity checks, although I wonder if that's out of date. There's another way we'll do it in the demonstration in a minute here. Anyway. HEMA L. All right. All right.